So guys, welcome back. In this class, I actually want to talk about simple harmonic motion. And I received from your comments that I should talk about the topic simple harmonic motion because you're having an exam soon and the difficulties you have been facing in simple harmonic motion. So I want to help you to find a bit of solution to those problems. So in this class, let's take the topic step by step. And after the class, we are going to solve a whole lot of questions together. So I need you to stick to the end. If the video is too long for the whole section, I'm going to break it into two or three. Just follow through and try to solve all these questions with us in order for you to understand. So the topic we want to look at is simple harmonic motion. A whole lot of times when you hear in physics that simple harmonic motion, simple AC circuit, you wonder that the topic says simple, but most students find it difficult. I don't know why. Maybe it's because of the basic principles of formulas here and there, but the topic is actually very simple. So let's take it step by step. These are things you have done before. Many of you, when you were in secondary school, you took a ball attached to a rope or a swing, then you pull the ball to one side, then you let go. Then the ball actually continued a motion in which the body goes from one point to the other. So it starts from a point, covers that point, then come back again. That is simply simple harmonic motion, although the mathematics sounds more complicated than what I just said. So let's look at what it is. So definition is the first thing we're going to treat. Some systems that exhibit simple harmonic motion and some terms we use in treating simple harmonic motion. The energy conservation of simple harmonic motion, velocity at position x. They can say calculate the velocity at a particular position. That means there is a change in velocity in a simple harmonic motion. Then they can say calculate the maximum velocity. And so let's quickly look at this. What do we mean by simple harmonic motion? Let me take it slowly. So calm down, breathe, take your pen and write. Let's take it step by step. So the definition, simple harmonic motion is simply defined as the periodic motion of a body or the to and fro movement of a body in which the acceleration of that body is directly proportional to its displacement under the action of a restoring force. There are some terms I've said here. First is the acceleration of the body is directly proportional to its displacement. We are going to understand what this guy means as we are moving on. And this always happens under the action of what? A restoring force. So these are terms you should not forget. What does restoring force means? What does displacement means? What does acceleration means? So let's check it out. Now let's say you have a swing like this. This is a ball. Then you put the ball to a side. As you put the ball to this side, this is where the ball is. Now that position from if you allow this ball to stay on its own, it's going to remain like this. It's not going to pull itself to this side. You are the one that pulled it to this side. Now that position where it will remain at rest, that position is called the equilibrium position. So that position that it will normally stay without you displacing it is called the equilibrium position. Now you pull it to a side. You pulling it to a side means you are displacing it. You are changing its position. So that is called what? Displacement. So from here to here is your what? Your displacement. But now when you pull it to this side and you let go, what happened to the ball? Very good. The ball will move back towards this position. So but it's not going to stop in this position. When it moves back, it gets here, then it continues its journey. So it will move and get back to this position. So now if you look at this body, the body will now continue to go to and fro, to and fro, to and fro. So that is what we call simple harmonic motion. Now what do we mean by this statement? Acceleration is directly proportional to displacement. You remember F is equal to ma. Definitely acceleration is under the influence of a force. Now when I pull this body up, the body wants to go back to its position. The more I pull it, the more it wants to force itself back under gravity. So there's a force that is trying to pull it back. And so you can see now I'm pulling it to this side, but it's trying to go back to where I'm pulling it from. That means that it's the direction of motion of this body naturally. We always want to counter my own displacement. As I'm pulling it this way, the body wants to move back. So now, the more I pull it, the more it's ready to take itself back to that position. That's why we say that the acceleration is direct proportional to its displacement, because the more you pull it, the more it wants to run back. Now, if I introduce a constant here, my acceleration is going to be equal to minus omega square x. This is one formula you should note in your notes. That's our first formula. So our acceleration is equal to minus omega square x. Omega is angular velocity and is a constant here. When I start the class from beginning and I take it slowly, we're going to derive this formula. So stick to the channel. So now, from what we have here, what does this negative actually indicate? If you would have reasoned that, you know that I displaced it, but where is it going? Opposite direction. So now, the negative shows that if I displace the body always wants to take itself back to where I displaced it from, which is opposite to my own displacement. That's what the negative indicates. And don't forget, what force is bringing it back to this equilibrium position? That force is called what? Restoring force. So now, that is the definition dealt with. Now, what are the systems and terms we use when we are describing simple harmonic motion? There are several systems. You can imagine your heartbeat. It goes, so it keeps beating periodically. So it continues to complete a circle. And you talk more about that in biology. So your heartbeat also exhibits simple harmonic motion. You can imagine you have a mass on a spring. This is a spring. So this mass is on a spring. If I pull this mass down, this mass of a body or a block, so I pull this block down, then I let go, what do you think will happen? By the time I pull it to this position and I let go, you notice something, that this body, by the time I let go, it will come back to this position, then spring up a bit, then come back to that equilibrium position, then go down. So it will cover a displacement. Do you understand that? Then it will also go back up, compressing that spring up, then covers another displacement. I hope you're getting my point. So when I pull it down and I let go, so it keeps going up and down, up and down. So mass on a spring is also another example. Mass on a spring. I already said your heartbeat. Now, what do we call this? We call this what? A simple pendulum. So a simple pendulum also exhibits what we call simple harmonic motion. So mass on a spring, a simple pendulum. It does not end there. Now, you can have what we call a loaded test tube. Loaded test tube. So if you have test tubes and probably you have a liquid and you load the test tube up with some lead shots or some masses, and you load the test tube and you now allow it to balance in the liquid, then you push it down, you displace it. By the time you let go, what happens to this tube? You notice it keeps oscillating up and down, up and down, up and down. It means a loaded test tube, a simple pendulum, a mass on a spring, your heartbeat, all these are systems that exhibit simple harmonic motion. Now, what are the terms you hear often on simple harmonic motion? I already talked about one, acceleration, the rate of change of the velocity, Abi. So now, acceleration, the displacement is just the position you are pushing the body to. Then the restoring force. Now, another thing is what we call amplitude. So let's look at those terms one after the other quickly. In order to make the question, or in order to make our mathematics easier, I will represent all these I'm saying with just a single line, just to make your math easier. You will understand everything I'm saying. So now, so if I have a straight line, let's say I have a straight line like this, and this line represents, the center of this line represents my E. What do you think my E is? The equilibrium position. Like if I pull the body and I let go, it goes back to E, then goes back to this place. Let's call this A and let's call this B, meaning that the position I pulled it to, like now, let me just give you a brief analogy. So this is a body, I pull it to this position. So now the body will swing forth and back. So back to this E. So this is where I'm representing as the E. This is where I'm representing as B. And this is where I'm representing as A. So please follow this through so that you get the concept clear and understand what we're about to do. So now when I pull this body to this side, the body goes back to E, then to A, from A back to B, B to A to B. So that's the simple harmonic motion. So now when I put it from E to B, I displaced it from here to here. Now that is the maximum position I'm displacing it to. We call that part A. And what does that A mean? So please, let me use another term here. Let's say C here. So let's say C here so that you don't get the concepts mixed up. So now A represents what we call amplitude. So you can write in your notes, what does amplitude means? An amplitude is the maximum displacement from the equilibrium position. This is the equilibrium position. So the maximum position you will displace it to is what we call what? Amplitude. So the maximum displacement from the equilibrium position. And now amplitude is usually, the unit is a meter, definitely, since it represents distance. So meaning that if I go back to my straight line, from here to here represents my amplitude. Is that taken? So there's another position, X. Any position in between the equilibrium position and this B, that represents my X. So let's say this is where I pull the body. So I put the body to this position from here. At a point it will get to this position. So that means I can know the distance from here to here. Let's call that X again. So let's say I pulled it, then this place from here to here is X. Do you think X represents my amplitude? No. X is just a distance in between E and B, meaning that in between the maximum displacement. So this is where the body is now. So that position where the body is, let's call it D. So the distance from E to D is called X. So that is this position now where this body is. So take my A to a side. So let's call this D. Please, let's follow this so that you will get the concept of how to solve questions when you are dealing with questions. So this position is called the D, like I'm representing it with D. So meaning that when I move it from E to B, it will cover the position it will get to D. So the distance from equilibrium position to that D is what we represent as X. While the distance position from E to B, that one is represented as A, which means the maximum displacement. I'm using one side, it's the same thing on both sides. So A means the same because it covers the same distance periodically. So that is one term. So the term we have talked about now is acceleration, displacement, the maximum displacement. So please look at this very well again and try to revise what I've just said. So let's go on. So now the next thing they can say is that what is the velocity of this body? That's another term, velocity. So definitely if you move this body from here to here and you let go, that means that it's going to stop here. And when a body comes to a stop, what do you think that is? The velocity is going to be 0. So at this point now, the speed of this is going to be 0. So at B, the speed is going to be 0. At C, the speed is going to be what? 0. Let's note this. We are going to be doing some calculations. So at B now, so it's going to be what? It's going to be 0. The speed will be 0. So now, if I let this thing go, so what will happen to that body? Very good. You know acceleration is directly proportional to the displacement. So if I let go, it will speed down, meaning that the speed will start increasing. So let me first bring this back. At B now, our velocity is going to be 0. I hope you're getting that. Now, when I let go, it will start speeding down. When you get to this E now, that's the equilibrium position, it's going to speed up. So by the time it gets here, it's coming with great speed. So its maximum speed will be at E. Then it is that speed it will take up again. Then when it gets to C, the V will become 0 again. Then it will come back. So meaning that the maximum speed, well, let's represent it with V sub max. So the maximum speed is at E. Let's not forget that. So the V is 0 at what? At B. Please just try to follow this one after the other. So now, meaning that from B to E now, the speed will continue to increase. So the speed that, let's say this is D, let me even do another position that this is F. So the speed from B will start increasing. So the speed at D will be greater than the speed at F. Let me repeat that. The speed at D will be greater than the speed at F, because the speed started from 0, then it started increasing. So the speed at D will be greater than the speed at F. Although you are going to be asked to calculate speed in between, we are going to see how to do that. But I just want us to understand these terms very well before we start doing some bit of calculations. So as you, let me repeat that. Speed at B is going to be what? Very good, 0. Speed at E is going to be what? Maximum. Speed in between can be calculated, but the speed increase from B to where? To E. And when it's going out from E to C, the speed start decreasing. Then when it gets to C, the speed becomes 0. Then the speed start from 0 again, moving back. Then the speed gets to E, which is maximum again. So that's what we have here. So our maximum speed is at E, then the 0 speed is at what? At B, because the body will come to a rest. So that talks about the speed. You are going to see the formula to calculate the speed and everything. Let's note this formula first.